Introducing implicit functions. This section forms the merit part of the first year for the Foundation Engineering Maths course. This introduction can then be followed by attempting the exercises, and solutions will appear on video. So implicit functions, in the formula y equals 4x squared plus 3, where the dependent variable y is explicitly expressed in terms of the independent variable x. This means the function is explicit if we can write y equals something. In other words, y equals 4x squared plus 3 is an implicit formula because it reads y equals something. It's not always desirable or even possible to rewrite a function explicitly like this. For example, if we look at these, now I don't know whether or not on the video this is going to come out to be a circle, because I think it's something to do with the way that the screen's orientated. But the first example here is the equation for a circle, and it's of this form. Look, x minus a squared plus y minus b all squared equals r squared, where a and b give the x and y coordinates for the center of the circle, and r is the radius of the circle. You can see it wouldn't be straightforward to rewrite this formula in the terms y equals something. There's another example for an ellipse. X squared over a squared plus y squared over b squared equals 1. This particular ellipse is centered around 0, and by changing the values of a and b, I would make the ellipse taller and narrower or wider. Again, not an easy function to express in terms of y. And finally, the equation for a hyperbola, almost the same as an ellipse rather, but x squared over a squared minus y squared over b squared equals 1. These formulae are all written implicitly. Useful but inconvenient to write them explicitly. We could write these explicitly, but it's more useful in this form because you can see how a and b would change the shape of the hyperbola or the ellipse or the position of the center of the circle. So these are implicit formulae. They're not written in the form of y equals something or x equals something. We need to be able to differentiate functions like these without trying to write them explicitly. Luckily, this turns out to be reasonably straightforward. So if I have some function fy, where y is the variable, so this is a function in terms of y, and I want to differentiate, say, with respect to x, some other variable, i.e. I want to find, and if you look at the notation here, this means I've got a function involving y here, and I want to differentiate it in terms of x. So I want to find d by dx of fy. I differentiate with respect to y. I must do that because this is the variable. So if I want to differentiate with respect to y. But then I multiply by dy by dx. In other words, I write this. D by dx of fy equals d by dy of fy. In other words, I differentiate in terms of the variable that's inside the function. But then I multiply by dy by dx. Now, if you look at this algebraically, although this notation isn't algebraic, if you look at this, those dy's cancel, and I'm effectively finding d by dx of the function. And that's how it works. If you look at the chapter, and you'll see at the beginning, it's all to do with use of the function rule, or the chain rule. So let's have a look at some examples of how this works. That's probably the easiest way to see how they go. So, for example, I want to find what's the differential in terms of x of a function in terms of y, 3y squared. So what do? I find d by dy of 3y squared, but then I multiply that by dy by dx, the new variable that I want to differentiate it in terms of. And this equals, what's the differential in terms of y with respect to y of 3y squared? 6y dy by dx. So the answer is 6y times by the differential of y with respect to x. Not too bad. We'll see how this becomes useful later on. Another function, another example. See if you can do this one yourself and then have a look at my solution. I want to differentiate a function in terms of y, 3e to the 4y, with respect to a new variable t. So this equals d by dy of the function 3e to the 4y times by dy by dt, which is going to equal differentiating 3e to the 4y with respect to y, give me 12e to the 4y times dy by dt. Try this example and then have a look at my solution underneath. Differentiate the function 4 log to the 5t, or log of 5t rather, with respect to x. So it will equal d by dt of 4 log 5t times by dt by dx. So this equals log of 5, differential of log 5t is 1 over t, so this becomes 4 over t times dt by dx. Now try some of the questions in exercise 176, page 444. And as I say, solutions will appear on video link.